Ancient mathematics was very different than the mathematics you're used to today. Two primary tools ancient mathematicians used were the compass and the straightedge. With these two simple objects, they made an astounding number of proofs and mathematical discoveries. However, there were some problems that were always beyond their grasp. Learn more about squaring the circle and the problem that eluded mathematicians for over 2,000 years on this episode of Everything Everywhere Daily. This episode is sponsored by ButcherBox. Thanksgiving is right around the corner, and that means Thanksgiving dinner for friends and family. A Thanksgiving dinner can be a massive ordeal and a nerve-wracking affair. You have to buy all the food and spend the better part of a day preparing everything before serving it. So, why not take one thing off your plate by letting ButcherBox take care of the centerpiece of your Thanksgiving meal, the turkey? Not only will ButcherBox deliver the turkey directly to your door, but they will also offer some of the highest quality turkeys that you can find. Their turkeys are never given antibiotics or hormones, and they're all certified to be raised humanely. And in addition to turkey, they also have ham, beef, and seafood if that's what you prefer. New ButcherBox members that sign up using my link will receive their choice between a whole turkey, turkey breast, or a spiral ham, plus $20 off when they visit butcherbox.com/daily and enter code DAILY at checkout. Once again, that's butcherbox.com/daily, code DAILY at checkout.
Is your cold making it hard for you to get to sleep and leading to a bad morning? Switch to Mucinex Night Shift for fast, powerful nighttime multi-symptom cold and flu relief. Mucinex Night Shift fights your worst nighttime symptoms to help you get to sleep and wake up ready to go. Mucinex Night Shift. It's comeback season. Use as directed.
Ancient Greek mathematicians were some of the first in the world to formalize mathematical thinking. Numbers and simple arithmetic existed before the Greeks, but one of the things that the Greeks gave to the world was the concept of the mathematical proof. Proofs are a sequence of logical arguments that derive a conclusion from accepted premises or axioms. Before formal proofs were established, early civilizations like the Babylonians and Egyptians used empirical methods to solve practical mathematical problems. They employed arithmetic rules and geometric procedures for practical tasks like construction, land measurement, and trade. Their approach to mathematics was more intuitive and lacked more formal deductive reasoning. The Egyptians used simple formulas for the areas and volumes of shapes, but these were based on approximations and observation rather than formal proof. Likewise, the Babylonians made advancements in algebra and geometry, particularly in solving quadratic equations and understanding Pythagorean triples, but they didn't yet employ deductive reasoning or proofs. So while the Greeks created the idea of the proof, which is the foundation of modern mathematics, their mathematics was a far cry from what we have today. For starters, they didn't use base 10 numbers like we do today. Their numbers were more like Roman numerals, which are notoriously difficult to manipulate. They didn't have zero or negative numbers, which made things even more difficult. Their mathematics wasn't really about number manipulation or calculation at all. They didn't have algebra, which Islamic mathematicians would invent centuries later. What the Greeks really excelled at was geometry. If you've ever taken a geometry course at any point in your life, there's a very good chance that what you studied came from Euclid 2,300 years ago. Their geometry was abstract, but it also had a very real, tangible element to it. The Greeks used two simple tools to do most of their geometry work: the compass and the straightedge. And you've probably used both of these tools at some point in your life. A straightedge is, just as the name implies, a straight edge. You probably used a ruler, but the actual measurement marks on the ruler are irrelevant to a straight edge. It could be totally blank. A compass is a tool for drawing circles or arcs. It typically consists of two hinged legs, one with a pointed end and the other with a pencil or a marking device. With just these two things, you can create an incredible number of shapes and prove theorems, such as constructing regular polygons, such as equilateral triangles, squares, and pentagons, bisecting angles and constructing perpendicular lines, and calculating areas and volumes of simple shapes. Within this Greek system, compass and straight edge constructions were not just a mathematical exercise, but a form of logical rigor. These constructions represented pure geometry, free from the complications of measurements or instruments beyond the idealized straight edge and compass. While the Greeks were able to do quite a bit with these simple tools, they couldn't do everything. In fact, there were a few problems that absolutely confounded the Greeks. In particular, there are three classic problems that no one could find a solution to using a straight edge and a compass. They were doubling the cube, trisecting the angle, and squaring the circle. All of these problems are relatively simple to state, but were fiendishly difficult to solve. The legend behind the doubling the cube problem, also known as the Delian problem, originates from ancient Greek mythology and centers on the island of Delos. According to the story, the people of Delos were suffering from a terrible plague and sought advice from the Oracle of Delphi. The oracle conveyed a message from the god Apollo, stating that to end the plague, they must double the size of their cubic altar. Taking the instruction literally, the Delians interpreted this to mean that they had to double the volume of the altar, which was the shape of a cube. The problem then became how to construct a cube with twice the volume of the original altar, using only the basic geometric tools of the time, a compass and a straight edge. Despite their best efforts, the ancient Greeks struggled to find a solution, as simply doubling the side length of the cube would result in a cube 8 times the volume, not twice the volume. This challenge is passed down through generations of mathematicians who attempted to solve it as a geometric puzzle. And the legend behind it highlights both the reverence the Greeks held for geometry and their belief in divine guidance to solve practical and spiritual problems. Ultimately, it wasn't until the 19th century that the problem was proven impossible to solve using classical geometric methods. The other problem, the trisecting the angle problem, is a classical challenge in geometry that involves dividing an arbitrary angle into 3 parts, or trisecting it, using only a compass and a straight edge. Bisecting an angle into 2 had been solved in antiquity. It's a relatively easy process. While it's possible to trisect certain specific angles, such as a right angle, the general problem of trisecting any given angle could not be solved with just these tools. Mathematicians like Hippias and Archimedes explored mechanical methods to approach the problem, using such curves or other tools beyond the compass and the straight edge, but the Greeks were unable to solve it within the constraints of their geometric rules and proofs. The impossibility of trisecting an arbitrary angle was formally proven in the 19th century, when it was shown that certain angle divisions require solving cubic equations, which cannot be done with just a compass and straight edge. This is because only numbers that are solution to certain types of quadratic equations can be constructed using these classical tools, and cubic equations, like those arising from angle trisection, fall outside of this range. Finally, we get to the third problem, which is the most famous of the 3 and has become a metaphor for unsolvable problems: the squaring of the circle. This challenge is deceptively simple. Construct a square with the same area as a given circle using a compass and straight edge in only a finite number of steps. That sounds really easy. However, it is anything but. One of the earliest recorded figures to attempt squaring the circle was the Greek philosopher Anaxagoras. In the early 5th century BC, he worked on the problem while imprisoned, making him one of the first known mathematicians to grapple with the challenge. Anaxagoras' work was based on intuition and approximations, and although he didn't solve the problem, his effort illustrates the problem's appeal to ancient thinkers. In the late 5th century BC, Hippocrates of Chios made significant progress by discovering that certain curved shapes, known as lunes, or moon-shaped figures bound by arcs, could be squared. His work showed that it was possible to square some segments of a circle, raising hopes that the full circle could be squared. Hippocrates' discovery was important for later studies, but ultimately his method could not be extended to the whole circle. Around the same time, Antiphon, a contemporary of Hippocrates, suggested an interesting approach by inscribing regular polygons inside of a circle. He hypothesized that by increasing the number of sides of the polygon, it would eventually coincide with the circle, thus allowing one to approximate the area of the circle. If this sounds familiar, he developed a very early form of what would eventually become integral calculus. In the 3rd century BC, Euclid published his monumental work, The Elements, which systematized the rules of geometry. Euclid outlined a rigorous system of geometric constructions that relied on just the compass and straightedge, defining the rules that would constrain all future attempts to square the circle. Euclid could not provide a solution to the problem, but at least solidified the importance of providing geometric constructions through logical deduction rather than just trial and error. The Elements became the standard reference for geometric work for over 2,000 years, and squaring the circle remained an open challenge within this framework. During the Middle Ages, particularly in the Islamic Golden Age from the 8th to the 4th century, mathematicians preserved Greek mathematical texts and expanded on them. Although there were no major breakthroughs in solving the problem of squaring the circle, Islamic mathematicians such as Al-Khwarizmi and Omar Khayyam made important contributions to algebra and geometry, setting the stage for future developments. Some mathematicians explored more sophisticated geometric methods and improved approximations of pi, but they did not resolve the fundamental problem. The work of the Islamic scholars was transmitted to Europe during the Renaissance, where it reignited interest in classical problems like squaring the circle. At this point, mathematicians realized that the issue was not really with any technique with a compass and straightedge per se. It all had to do with the number pi. You can easily create an equation showing the area of a square equaling the area of a circle. The area of a square is s squared, where s is one of the sides. The area of a circle is pi r squared, where r is the radius. Set them equal to each other and divide each side by r squared, and you get s squared over r squared equals pi. The secret to solving the puzzle was figuring out the nature of pi. Throughout the Renaissance, mathematicians attacked the problem by trying to figure out this nature of pi. Much of this involved calculating pi to more and more digits. And while that was helpful, it didn't really tell you anything about the nature of pi. One big breakthrough that would be a big step towards resolving the problem was taken by Gottfried Leibniz in 1682, who found the function of sine x was not algebraic. And that means you couldn't solve it by using algebraic operations such as addition, subtraction, multiplication, and division. This was the first case of a proof that some things could not be solved algebraically. Numbers that couldn't be expressed algebraically were called transcendental numbers. In 1768, Johann Heinrich Lambert proposed, but did not prove, that pi and e were both transcendental numbers. This hypothesis was important because, if it was true, it would mean that squaring the circle was in fact impossible. Lambert also proved that pi was at least an irrational number, meaning it couldn't be expressed as a fraction using whole numbers. After almost 2,000 years of fruitless attempts at squaring the circle, the decisive breakthrough came in 1882 when German mathematician Ferdinand von Lindemann proved that pi was in fact a transcendental number. This result was built upon by earlier work by the French mathematician Charles Hermite, who had shown that the number e, the base of natural logarithms, was transcendental. And this was the final straw. After 2,000 years of trying, it turned out that everyone who was trying to square the circle was wasting their time, because it was impossible to do. The centuries of pursuit of trying to square the circle ended up being futile, but it wasn't a total waste. In the process, there was a great deal that was learned about geometry, algebra, and the number pi. In the end, despite being a relatively simple problem to state, squaring the circle was shown to be impossible. The ultimate lesson was that some problems, no matter how simple they may seem, can never be solved. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Benji Long and Cameron Kieffer. I want to give a big shout out to everyone who supports the show over on Patreon, including the show's producers. Your support helps me put out a show every single day. And also, Patreon is currently the only place where Everything Everywhere Daily merchandise is available to the top tier of supporters. If you'd like to talk to other listeners of the show and members of the Completionist Club, you can join the Everything Everywhere Daily Facebook group or Discord server. Links to everything are in the show notes.